Regrowing Native Valves and Vessels. What a wonderful concept. And I'm with Laurent Grandidier, and he is the CEO of a company called Xeltis, Xeltis, Zurich, Switzerland. What a wonderful concept, growing stuff essentially in a tube for everybody else to use, using natural material from ourselves. How long has this been going on? About 15 to 20 years that you've been working on this?
Exactly. So, Rick, it's been actually this concept started in the 90s out of a group at the Harvard Medical School, where a group of physicians were working on regenerative medicine and more particularly on tissue engineering. So the concept of tissue engineering is to regrow organs or parts of organs outside of the body. And two of these professors came back to Switzerland after their time in Boston and continued working on tissue engineering for cardiovascular implants, which are either heart valves or blood vessels. The whole objective, if you want, with the field of regenerative medicine is to be able to provide solutions for a lifetime to the patients, which means essentially implants that will have the same regenerative capacity as the original implant, but also implants that will be made out of the regrown tissue from the patient, so that ultimately the patient's blood cells are only in contact with his own cells, so no foreign body in the implant.
Using pediatrics as a starting point, where would it fit with a patient like that?
So that's a very good example. So pediatrics, what happens, you have a very critical need, especially in young patients suffering from congenital heart disease. These patients need to be operated when they're very young, and obviously they will grow very fast in their first years of life. The problem is with current implants, which are made either of plastic or animal tissue, of course, they won't grow, which means that the patients will outgrow their graft, requiring multiple operations. And when we talk about open heart surgery, well, that's not something you can do an unlimited number of times, which really leads to dramatic situations.
Now, in generating tissues, cells are obviously important, but you're finding that there's something maybe even more important than cells. What is it?
You're absolutely right. So what we learned throughout these 20 years of research on tissue engineering is that, of course, cells are very important, but our hypothesis, which you are now validating, is that even more importantly than the cells that you regrow in tissue engineering is the scaffold, so the matrix, which is being constructed while the tissue are reforming. So while we started to understand this fundamental importance of the matrix, we started looking at removing, for example, cells from our tissue engineering constructs, which we knew were regrowing, attracting cells. So we thought, okay, let's kill the cells, see what happens. So we published, the University of Eindhoven, University of Zurich, published together a very interesting paper recently showing some very promising results of this. But a few years back, we thought, okay, the ultimate solution would be to have a decellularized construct, but which is made only of a synthetic material. So we started working on, based on groundbreaking polymer research at the University of Eindhoven, we started working on finding a new material that would be able to sustain the very high mechanical characteristics required for a heart valve, for example, while having the right extremely high porosity that is required for tissue engineering to happen in the body. So you want a polymer that is strong, that is durable, that is very porous, and also that is biodegradable. And so this equation was solved last year by our group, and we're very proud of this. It was solved last year, was proven earlier on this year with the first acute animal trials showing very promising tissue regrowth and the biodegradation of the polymer, and was really thanks to this, both the tissue engineering know-how, because we have built hundreds of tissue engineering constructs, so we really understand what's happening when tissue regrows or reforms, but also thanks to this polymer research and new type of material and production methods as well.
Now, we're at EuroPCR. What did you present here specifically? I mean, for a CEO to be standing up in front of all these doctors, I thought it was wonderful. What were you talking about?
Yeah, it was a very interesting experience. It was the first time I was presenting to a large medical audience. So it was very interesting, actually, because I used this, well, first to present the very recent results, which we had, very interesting, but also to show an illustration of how medical innovation comes to life. Because, for over 15 years, the company and the different academic partners have been working on let's say, exploring. I call this the exploration time, where we looked at technology, applications, but really the big change was last year when we built the organization and we said, to evaluate all the exploration we've been through, we have to add not only technology and applications, but add as well the regulatory pathway and the health economics, which are extremely important today. And so it's out of this evaluation phase that we decided to focus our efforts on this new, we call it the CORE platform, cardiovascular organ regeneration platform, COR. Also, it means the heart in Latin. So we found it's a very beautiful name for our new technology.
I think this is wonderful. And you can read more about this, by the way, in Cardiosaurus World News and Cardiosaurus Interventional News. And for Xeltis, Laurent Grandidier, I'm Rick McGuire.